So if you haven't met me, my name is Jin. I am holding down the fort for this classroom today, and Megger, Volney from Megger will be presenting about substation testing today. I'll let Volney tell you a little bit about himself and let the presentation roll. And because of that raffle and everything, there might be some people rolling in just slowly. So yeah, just
okay.
anticipate that.
Thank you for being here. It's the last presentation of the day, so it's kind of the toughest one, but I appreciate you dedicating time to us. My background, I've been working in the electrical testing world since almost graduation from university. I was born in Colombia, South America, and then moved to the United States like 15 years ago. Started working here with a consulting company and doing testing in the field, substation testing, commissioning. And 7 years ago I moved with Megger and been working with them as an application engineer for the substation products. Megger has a wide, very broad range of products. We cover relay testing, battery testing, substation testing, cable testing, and I focus on the substation products. So I'll be covering about how I can support the transformer testing, circuit breaker testing, battery testing, and power quality.
Okay.
For today, we have I have more slides than time. I have like 125 slides, so I guess you have a particular interest in this presentation. What topics or what testing do you guys normally do, or what is your field of work?
We do switchgear in commercial buildings and industrial factories and stuff.
Okay.
We shut down the switchgear and we test as much as possible.
Okay. All of you are from the same company?
Just us.
Okay. And what about you guys?
We do like breakers, transformers, relays.
Okay. Perfect. Okay. Good. So very likely you're gonna see a lot of interest or see a lot of good on this presentation. So we have instruments that can work in all of these to work with all of these customers. So for utilities, service providers, industrial OEMs, and our instruments can be used in any of these maintenance practices: corrective maintenance, periodic, preventive, predictive, and focused on the substations. We have instruments that you can use for transformers, instrument transformers, circuit breakers, batteries, relays, pushing step changers, and many other instruments or equipment inside the substation. So the very first one that I want to present is it's a very basic test, but very helpful and very common test in the substation world. Which is the low resistance measurement or the contact resistance measurement. When you use this, well, you use this when you're commissioning new installations. You want to use it for circuit breaker testing. Doesn't matter what type of breaker, low, medium, high voltage. You use it also to check the bus bar connections, that everything is well connected in a bus bar. You can also use it to detect manufacturing defects, welded joints, connections. You can see to determine if they're well done or not. And it's also used in switchgear, cables, high voltage installations, railway lines, the wind jet turbines to test that from tip to tip everything is in good condition for the wind generators. In many other applications, we get sometimes a lot of calls related to very specific applications. So to see what other applications or to determine how things can work with this test, well, this is the principle of measurement. You have a resistance, the sample that you want to measure, and you apply a current. It's DC current. And when you have current circulating through that sample, you measure the voltage drop exactly at the point or between the 2 points that you want to determine the resistance. And with that voltage drop and that current, well, using Ohm's law, you can determine the resistance of the element that you want to test. So voltage drop is measured, or current is known from the instrument that you're using, and the instrument calculates the resistance. Very basic, but very helpful test, and you can detect degradation between contacts, excessive vibration, changes in temperature. You can also use this type of test to determine of the effects of changes in temperature. You can see if there's, or you can also determine that there's been chemical corrosion, loss of torque, very important for battery testing as well, to determine the strap resistance. It's very important to measure the resistance of connections, because basically that will represent losses. If you have losses in your connection, that means a hotspot, and hotspot will mean degradation of your connection. So reduce efficiency, increase cost, and heating damage. You will get damage because of heating causes. The different places where you can apply this: motor windings, circuit breakers, we already mentioned that, switches, welds, coils, batteries, straps. There's a challenge when measuring a low resistance. First of all, you might test the lead resistance, so you need to know how to use the leads and to use the leads appropriately to not influence your result from the lead connection. And you can also have external influences, so like thermal effects or electromagnetic influence, and additional current that might be circulating if you're doing a test on a battery, for example. So to get the proper measurement, to get an accurate value, basically you use what is called the 4-wire method. This method, with that you can eliminate the errors due to the connection or to the leads. Basically you have a current injection, leads, and separate potential probes. And this is the method that you use when you have to measure resistances below 10 ohms. And one thing that you have to always consider is that the potential probes have to be always inside the current that you are applying. Because if you put the probes outside the current, you're, in addition to the voltage drop due to the resistance, you are going to measure the voltage from the instrument that it's applying to circulate the current. So that will influence your result. So that is, when you have separate leads, you have to always connect the potential leads inside the current connection. There are leads that come already, everything is integrated, so that won't cause any problems. Another thing that you have to consider when measuring resistance is that if you have some kind of noise here or signal going through that resistance, you have to use what is called the forward and reverse mode. So basically you perform, because this is DC measurement or DC current, you apply the current on one direction and get a result, and then you reverse the connection and you get the result in the other direction, and then everything is averaged to be able to get a good result. Yes?
Wire measurement, how do you eliminate potential induced voltages that you're unaware of?
Induced voltages,
Magnetically induced voltage.
So basically you are averaging, or you are considering the effect in one direction and subtracting from the other direction, and then you get your actual result. And this is one easy way to see it is when you are performing measurements of strap resistances in batteries. So in batteries you will have current flowing in this direction, so that will affect your measurement, but then you measure in the other direction and you get a reversed measurement, and you subtract or average that, and you get your result. There's different modes that you can have in your instrument. So normal measurement, basically, you connect your leads, you start the test, and the measurement is obtained. So the test finishes right after obtaining a value. And in this mode, you can have the forward and reverse feature as well. The continuous mode, this is more like to test a switch gear. For example, you connect from one end to the other the current of the switch gear, and then you go and measure different points. So you connect the leads, and every 3 seconds it will obtain a result. So you can go and test and do some adjustments if you want to the sample. And the automatic mode, the current leads are always connected, and the measurement starts when you connect the potential leads. Every time you connect the potential leads at different points, you get a different resistance value. So the instruments will have different modes, so depending on what application or what you are testing, you can obtain your results faster or easier. When testing circuit breakers, then, well, there's standards that mention or guide what to do and how to do the test on circuit breakers. And especially on the dead tag breakers that have the CTs mounted on the bushings, because everything is connected to the protection system. If you have a very high current change here, the protection will trip. Even though it's offline test, the protection is still connected, and you might trip the breaker because of the current, because the CTs are connected there. So you want to use an instrument that has a very soft ramp, and it doesn't affect the protection system. And you want to have also a very clean signal, so you don't have high ripple there. So then you can't use just any low resistance measurement instrument. You have to use something that has a very good signal and can handle the ramp of the current that you are injecting. So what we have for this purpose is the DLRO 100. It's a unit that can inject 100 amps. So this test, you can run the test with any current that you want. Depends on what you are testing, the selection of the current. Basically, the concept that you have to follow to select the current that you want to use for the test is never to exceed the nominal current of what you are testing. Because if you have a higher current than the nominal value, then your resistance will heat up. And if a resistance heats up, the resistance value will change. So you always want to be below the nominal current. Now, why 100 amps? Well, because of these standards for circuit breakers, that's the requirement for those standards. Circuit breakers should be tested with at least 100 amps or never to exceed the nominal current. So this is kind of pretty much the standard value of current for the instruments. We have instruments that can do 10 amps, or they can do 200 or 600 amps. Yes.
When you say nominal current, are you meaning the breaker's rated amperage?
Yes.
So if it's a 100 amp breaker or 1500 amp breaker, then 1500 amps?
Yes, so basically any breaker below 100 amps, you need to test with lower current.
Okay. So if you're testing a 20 amp breaker,
you
want to go past 20 amps. You dial this thing down.
Yes, because first,
it's like 10 or something.
Exactly, because everything in the breaker will start heating up because of that high current. You are exceeding the nominal rating of the breaker. Okay. Now, if it is for something else, not a breaker, basically just consider any nominal current or rating that has, because if you have higher current, well, it will heat up that sample. Okay. So this unit is battery operated, it's 17 pounds and very easy to set up. This dial here is for the different modes that we have. So we have the continuous, the automatic, and the normal mode. And here, this other dial is for the settings. So it has the 100 amp settings. Here will be this setting. This is 50 amps, this is 10 amps. But in any of these positions, you can use these arrows to change the current value. So you can be in the 100 amp setting, but you can change the current to 50 amps or to, in steps of 1 amp starting from 10. So here you have your current leads, and here you have your potential leads. So you can do the measurement as I was showing before. And one other feature that you have with this instrument is that you can have the sample that you are testing connected to ground on both sides. So this is a very specific application for breakers. When you are in this type of breakers, you need the safety procedures always ask to ground both sides of the breaker, because there's going to be a lot of induction and noise in the substation, induced voltages. So both sides of the breaker should be grounded, and whenever you're running the test, you need to lift one of the grounds. That kind of defeats the safety purpose of those grounds. So with this instrument, you can still have the breaker grounded on both sides and run the test. For that, you have to use an accessory, which is a clamp, a CT clamp, current clamp, that will determine how much current is flowing to ground and will subtract that from the actual current that the instrument is using. If we go back to the concept here, you're applying a current, and you want to, the instrument doesn't know if the current is going through the sample or not. So if there's another path for the current to flow, you need to tell, or the instrument needs to know what is the real current that is going through the sample to be able to use the Ohm's law and calculate it. So with a CT, with an extra CT here on this ground path, you can measure the current and determine the actual value that is going through the breaker, and you can test with the breaker grounded, which is a safer test. One other nice feature that this instrument has is that it is battery operated. Traditionally, the high current ohm meters, they are always connected to AC power. With this one, you have a battery and you can bring it up in kind of the breakers that are very high, and so you don't need to have an extension cord there. It's easy to connect and easy to use in that environment. It's Cat4 600 volts and IP54 operational, so you can, in rough conditions of weather, you can still use it. This, I was mentioning that you need a very smooth curve, and you need a ramp, an easy ramp. So this instrument, this is an actual oscilloscope screenshot of the signal, and you see that you have a very smooth, very well rectified signal output. And this ramp, you can adjust it. It can be here, it's kind of a 5-second ramp, but that ramp can be adjusted up to 15-second ramp. So it's going to be a very smooth ramp. It won't affect any protection system in the breaker or element that you are testing. That is in relation to low resistance measurement. Any question?
Why would you change the ramp? Did you touch on that? Why would you change the ramp up?
Well, if you don't have something that is going to be affected by the ramp, you can do a very quick injection and it's going to be a faster test.
Okay.
So if you have a protection system involved in what you are testing, you want a smoother curve so it doesn't trip the protection, and it's going to be a longer test. It's going to increase 15 seconds here, 15 seconds here, plus the time of the measurement, but you are going to be able to perform the test without affecting the
If you've
system.
got dozens of tests to make and you need to get it done faster, you can try to shorten the ramp.
If you don't have a ramp and you have an inductive load, inductive thing you're testing, you get a high, very large spike, which can trip the protection.
Well, if you have an inductive load, this is not the appropriate instrument to use for that, we have what it's called the transformer ohm meter, or transformer ohm meter, which is basically the same concept, but it has a higher voltage that can handle that inductance, and it has higher energy to load that inductance and reduce the effect of the inductance, and then get the value of the resistance. And I have this later on in the presentation. Okay. So, well, another feature that I didn't see here is that this instrument, you can control it from the actual instrument, or you can do a remote control from a computer connected to a USB port that it has here on the side. So you can have everything downloaded or captured while you are testing in the computer. So as soon as you finish the test, you have your test report. Or you can save results here and then download the results into a PowerDB report, and then you can have your report also very quickly and very professional report after you test or after you complete your tests. So low voltage circuit breakers. You mentioned the switch gears. I don't know if you guys do also low voltage circuit breakers. So we, for this one, for low voltage circuit breakers, well, you need to do kind of this test. This is kind of the full spectrum of tests that you perform on low voltage circuit breakers. And depending on the breaker, you would do one test more, which is the trip device with the second injection. But the conducting path, well, we just talked about that, digital low resistance ohm meter. You can perform electrical insulation, DC insulation test, the famous Megger test. We're not supposed to use that Megger for the test, but that's how the industry handles it. The operating mechanism, we do a primary injection testing, and that's what we're going to be talking about in this section of the presentation. And when you perform the operating mechanism test, really with the primary injection test, you are also testing the trip device indirectly. Sometimes, depending on the breaker, depending on the requirements, there's a way to test the trip device separately from the operating mechanism, which is the secondary injection testing, and usually that is proprietary equipment. So whoever manufactures the breaker will sell you or provide the instrument to perform the secondary injection testing. So the good thing about the primary injection testing is that you test this, and you test the brain, which is the trip device, and you test the operating mechanism, which is the muscle of the breaker. Everything is integrated, and when you do the primary injection testing, you test everything. You test both of them.
The CTs too.
Yes,
Test
exactly.
the CTs too.
And sometimes it's, well, there are always CTs, but the signals that come out of the CTs are very low, so that is what is difficult to simulate with the secondary injection testing device, and that's why it has to be a proprietary equipment, like from the same manufacturer of the breaker. Now,
Yes,
so that's why it's better to do the primary injection testing. Now, one thing in the low voltage breaker world, you have what is called the molded case circuit breakers, or you have the airframe circuit breakers. The molded case circuit breakers, the trip device, it's not actually a device, it's more like an electromechanical actuate element, and in those ones you can't do the secondary injection testing, so you have to use primary injection. And we are talking about breakers that go from 5 amps to I would say 600 amps or 800 amps. I've seen molded case circuit breakers. So primary injection testing is basically that you inject actual fault current into the path of the breaker, and you wait for the breaker to operate according to the characteristics from the manufacturer. And this verifies the proper operation of all of the elements, including the current sensors that you mentioned before, and the interface to the trip device. So everything is checked in addition to the entire primary path. Depending on the configuration of the breaker or the elements that are inside the breaker, you can do the minimum pickup testing, you can do the time curve testing, instantaneous strip testing, and ground fault. So this is the characteristic curve of X, Y, and Z breaker. And this is what it is talking about. The minimum pickup testing is when the protection element will actuate or will start operating. And then the manufacturer is telling you that it should operate in this band or this other band depending on the breaker settings. So a traditional obstacle or difficulty testing circuit breakers is interpreting these curves, getting the actual operating times from the curve, and knowing what current to inject. So, and traditionally all the primary current injection test sets, it's pretty much a manual injection, a very manual operation. So with the instrument that we have now, you can do an automated test, and the instrument also, or the software that controls the instrument, will have the curves for the breaker. So you just look for the breaker in the database, it loads the curve, and with that, the settings are already there for the test. We can put them there. So these are the different standards that kind of regulate or all the guides to test the circuit breaker. So you have the ANSI NEMA AB4, you have ANSI C3750. All of these will show and explain what you need to do with a breaker and how to perform the test and what tests to perform. So in addition to the manual characteristic or the manual way to test, there are other kind of challenges. One is the input power requirement. So sometimes you need very high power to do the testing. The primary current injection test sets, they are not generators. So whatever you put on one side of the instrument, it is transforming that into a higher current, but a very low voltage. So sometimes it's not the instrument, it's the power supply that needs to be in good shape to be able to provide the good signal to the instrument so it can run the test. Because it is a transformer, basically inside of it, it's always going to be like a heavy equipment, and it's going to be of a good size. Then setting the target current is difficult. Once you set the current target manually, because of heating of the unit or signal input power problems, your current is going to decay. So you need to adjust manually. The instrument that I'm presenting today, it does it takes care of all of these issues, at least from the control side, automatically. It has a feedback that will adjust the current automatically, and it will maintain the current during the test without any problem. So this is what we call the smart primary injection unit, 225. That means that it can test breakers up to 225 amps nominal current. And for that, it can output up to 2000 amps. We have the unit down there. It's probably the size of this layout. And it's a little bit heavy, but really for the amount of current that it can put out, it's a very light unit compared to other options in the market. It's the smallest primary injection test set in the market. And it's the very first unit in the market to eliminate the variance. So as you can see, there's nothing in the unit to control it. Everything is controlled from a computer. And the unit will do the automatic regulation and automatic control of the current for the test. It is designed for switchgear commissioning, circuit breaker. You can even do CT commissioning. These 2000 amp are instantaneous, but the unit can do 500 amp continuous output. The breakers, the highest breaker that you can test with one unit is 225 amps. And for customers that know our products from our old products, this is replacing the CD832. It's like a third of the size and probably half of the weight of that previous unit. And so here you have this is the general picture of the instrument. This here is one of the outputs. It's a 75 amp output. Then you have these on the side, you have this output, which is the 2000 amp, and this in combination with this common point is the 125 output. So you have different options. As for output, the maximum output will be 500 amps at 3.5 volts. You can, the unit is controlled via a computer. You have also your communication with USB or Ethernet, so you have two options to communicate. And the unit can be daisy chained, so you can connect up to 4 units in parallel. And in this case, we have 3 units here, but we are only connecting 2. So you get basically twice the current. So you can get up to 4,000 amps with 2 units, or 4 units can give you up to 8,000 amps. So in some cases where you have bigger breakers, you can use several of the units to test. You can have one in your fleet, and then you can rent one more to be able to test higher breakers. Let's say that could be like a one way to configure them. They can be connected in parallel or series here at the output, so you can have higher current or higher voltage. And this is how the test results will show. So this is the actual screenshot of a curve from the circuit breaker, whatever was selected there. And these points that show here in green are the points or the test points where the breaker tripped. So because they are inside this band, they look green because that's a pass test, a pass result. And here we have some red values that the breaker didn't pass, so it took too long to trip. The result is out of the expected time of operation. So it's indicating if it is a pass or a fail right away after testing the breaker, and you have your professional report after completing the test. Any question? Nope. Okay. So as the title of the presentation indicates, this is latest technology. It's kind of unique in the market to have this type of unit to control or to test circuit breakers. And everything's automated. You have everything in the software. You don't have to deal with the curves. You don't have to deal with issues testing the circuit breaker. Then the next one is the instrument to test current transformers. So these are also very common in switch gears or any substation. CT testing basically has a lot of standards, and you have the main one is the IEEE C57 13.1, which is the field testing of relay current transformers. And you have also IEC standards for testing and for the design and the requirements of these breakers, of these CTs. The current transformers, you use them to reduce the value of a primary current to a value or a magnitude that can be handled by the meters, protective relays, and other instrumentation, so you can do the control of the system. The standard values are 5 amps or 1 amp. The most common one here in the US is 5 amps. And, well, and in addition to be able to provide information to the instrumentation or the control apparatus, well, current transformers they are used also to protect the personnel from the high voltages or the high voltage environment. And you can see them for special applications in metering, protection. Mainly these are kind of the two main CTs that you can find out there in the substation world. The tests that you perform in the CT, they're basically saturation, the ratio and polarity, winding resistance, insulation resistance. You perform demagnetization, and you should also, like separate tests, you can do AC insulation and dielectric frequency response. So, long time ago, these used to be done with separate instruments. So you would have a variac for the saturation test. You will use that variac also to do the ratio and the polarity, but in a different way. Winding resistance, you need a DC source to perform the winding resistance, the DC current source. Then you need a separate instrument to perform the insulation resistance. In the demagnetization, you also probably needed something else. So usually testing CTs was very demanding on the instruments that you needed to test, and it will take a lot of time to perform the test. Here we can see the insulation test. So basically you have your CT, you connect to primary and the secondary to ground, and you perform the test. Then you change the leads and you do primary to ground and secondary to ground. So there's 3 different tests that you perform on the CT for the insulation. The CT ratio and polarity, you apply voltage to the secondary winding of the CT, and you measure the induced voltage on the primary side. So this is performed with an AC source. The previous one was a DC source. Here you have the winding resistance. So you connect to the secondary winding of the CT, and you measure the winding resistance. So pretty much the same concept that we were talking before with the low resistance meter, with a little bit of the effect of the winding, not so high here. We'll talk about the inductive effect later. And then because you are using here DC current, this core is going to get magnetized. So that has to be demagnetized so it doesn't affect the other tests that you need to perform. So traditionally this was performed with a battery or with a DC current source, but you have to switch the leads, and it was kind of a cumbersome procedure. So after you do that, then you perform the AC test in which you apply the voltage to the secondary terminals of the CT, and you increase the voltage until you find the saturation point, and you get this curve that explains or shows when the CT is not going to be effective anymore. So a very important characteristic for the protection CTs, not so much for the metering CTs. In the metering CTs, it's more important to get the ratio. The ratio of the CT is very important in the metering ones, especially to know or determine if it is within the specs of the accuracy of the CT. And one more test that you perform in CTs is the burden of the that is connected to the CT. It's actually not a test on the CT, but it is a test to determine what is the resistance of the load that is connected to the CT. CTs have a specification related to the burden that can be connected. If the burden is too high, the CT won't be able to drive current through that resistance, and it will not perform correctly. So the burden connected to the CT has to be measured. So all of these tests, we have an instrument that can perform all of those tests with one single instrument. And depending on the CT, sometimes you will have multi-tab CT. So all of these tests, you will need to do that on all of the tabs. So that is also incrementing the time that you spend testing. With this instrument, you can connect all of the tabs and perform the test concurrently in all of them. So it takes like 10 to 15 minutes to run the test in the CT, which previously it was taking an hour or probably more to test with separate instruments. To perform the test, the instrument can provide up to 2,000 volts, so it can saturate the core of the CT. These, in addition to be able to test CTs, can also test VTs, like voltage transformers, or capacitive voltage transformers. And we have accuracy for both metering and protection class. So protection class CTs, they don't need to be that accurate. The specification, the standard specification is that they have to be 10% accurate when the nominal current is 20 times the nominal current. So it's not a high accuracy, but the metering side, they have to be very accurate. They have to be 0.3 or 0.2 or 0.1% accurate. And for that, you need a very accurate instrument to perform the measurement. So with one single instrument, we have both the capability to test both types of CTs. As I was mentioning, the instrument can perform the simultaneous measurements on all tabs, so it performs a faster measurement. And it can perform demagnetization on CTs, so it performs, and it can do demagnetization with AC signal or DC signal, so it can work very well with both. Some CTs, they have a very high saturation point, so going a little bit into the detail of these. So this knee point, we can see that the saturation is happening around, well, in this case is probably 100, 200, 400 volts probably here. So you need just 400 volts to saturate this CT. But there are CTs that saturate at 30 kilovolts. So that you don't have this goes only up to 2,000 volts. So to be able to saturate those CTs, you will need a very big source. So with a different technique that we developed, we can, by using a DC signal, we can saturate CTs that have a knee point up to 30 kilovolts. These are very kind of specific CTs, generation system CTs that will be able to withstand very high faults, and they have a very high saturation point. So with this instrument, you can test this type of CTs without any problem. As I mentioned, it's a one-time connection and one-button testing. You connect everything, and it runs all of the tests that I mentioned: insulation, winding resistance, demagnetization, saturation, and ratio and polarity. With one single run, one single button, you don't need to do anything else after you press the button. And it will generate a report at the end of the testing. So once you're done with the test, it also generates the PowerDB result. The concurrent testing here, you can see a CT tab, the 5 tabs of a CT. Everything is connected to the instrument on the secondary side, the primary side. And once you start the test, it will do all of the tabs at the same time, concurrently. So you get all of your results in a very short time. In addition to having those features of simultaneous testing, well, the instrument can do, if you don't have accurate information from the nameplate, you can run the test without the nameplate, and it can show you the the nameplate information. So it does nameplate guessing. It will do evaluation from all of the results. It will compare to the standard requirements, and it will tell you if it is a pass or a fail of the CT. You can get your ratio and phase angle error tables. You have the parallelogram for the metering CTs. So what I was mentioning about the ratio of metering CTs, that is compared to a parallelogram. Whatever result you get, the value is placed in a graph, and if it is out, or yes, it's outside the parallelogram, means that it doesn't have the accuracy for the metering application. If it is inside the parallelogram, it will be valid for metering purposes. And it can check the lead connection, so if you have any problem in the connections, it can tell you, and it will show you how to test, to connect the leads correctly. Yes?
What about nameplate guessing? You don't know what it is, you look it up and it will run a test, give you an indication of possibilities or ideally specifically.
From the saturation points and the ratios that you get, it will populate the nameplate. So for example, if it has a saturation point around 400 volts, it will classify that as a C400 CT. And from the ratios it gets, and if the errors are not too high, it will populate the different ratios of the CT of the different types.
So it'll give you values, it will give you branding and numbers.
No, it's just values.
Okay.
Yes.
Okay, thank you.
Okay, so a totally different topic. Stationary batteries. This is kind of an extensive topic. I can talk more on that. I have just like 5 or 7 minutes, so I'm gonna skip this one. If there's any special interest, I can talk to that after this. I want to talk about the transformer testing a little bit. So for transformer testing, power transformer testing, well, the idea is that this is the life, the curve of the life of a transformer with no operation. Basically, if you leave the transformer there sitting, at a certain point it will have an end of life. But transformer is in operation, so it has a different curve. So every time there's a stress or an event in the system, that will affect the life of the transformer. And at a certain point, those stresses will keep a value or an event that is very stressing, and that will end up the life of the transformer. So you want to perform periodic testing to determine that you can do something here and increase the characteristics or improve the characteristics of the transformer, and so it can have an extended life. And for that, there's a lot of aspects that you can test in a transformer. You can do bushings or radiator. Well, you have your radiators, and you have to, well, probably that you test different with infrared, but and especially the coils is what you are mainly interested in, the insulation of these coils. So for that, we can have all of these tests. You can perform turns ratio, winding resistance, insulation resistance, power factor, excitation current, core ground, dissolved gas analysis, leakage reactance. All of these tests are kind of part of the regular maintenance procedures. And you have additional testing that it's more like advanced tests. So you can have a sweep frequency response analysis, dielectric frequency response. This is for the insulation quality, to see if the insulation is in good shape. The sweep frequency response is to determine if there's any mechanical change inside the transformer. And dynamic resistance measurement is to determine the condition of the tap changer if you have a no-load tap changer. So transformer turns ratio, you apply a voltage on one side of the transformer, you measure the voltage on the other side of the transformer, and that relates to the number of turns on the primary side to the number of turns on the secondary side. That is a very basic test that you perform on a transformer. And you validate the design specifications with this test. And this is when you are accepting the transformer in maintenance environment. After the transformer has been operating, you can determine the present condition or see if there's any change in the trend. Or after a fault or after an event, you can check if the transformer is still in operating conditions or not. With the turns ratio test, you can also verify the different positions of the tap changers, if it is a de-energized or a LTC, like a low tap changer. And the test is performed usually with 8 volts to 250 volts. Once you get the result, you evaluate that to the nameplate value, and the maximum error allowed for this result is 0.5%. So it's a very easy test to analyze. You get the result very fast test, very quick test, and very easy to analyze. Now you have to perform this on the 3 phases, so the ideal thing is to use a 3-phase test set that can facilitate the testing and allow you to perform a very quick test. Then you do the winding resistance test. This is also a very basic test, but here is where you have a little bit of complication due to the inductance. So you apply a DC current through the winding, and you measure the voltage drop across the winding. But this winding has the inductive part. For that, now you're interested in this portion of the equation, but then you have the inductive part that depends on the current variation in time. So for this test, you need a very good source that is not changing the current while you are running the test. And that's 3 minutes or 0?
3 minutes.
Okay.
Yeah.
So you need a very good source that has a very stable current during the test. And if you have stable current, that means current is not changing in time. So that this will be 0. The inductive part disappears. And for this, you have, I mentioned, you need a very good source. That means that you have a source that, you need a source that has a very good compliance voltage. And the instrument that we talk about first, the DLRO, that has a very low voltage compliance. So there's a very specific instrument to perform winding resistance test, which is a transformerometer that can handle, that has a higher voltage. It has just 10 amps or 50 amps. We have 2 options. And the voltage is much higher than a regular DLRO. And then the other aspect during the test is that basically you are charging these inductance with energy. After you complete the test, you need to discharge that energy. If not, that will kick back and you can have an arc, or you can have an accident with that energy. So the instrument that you use to perform a winding resistance, that has to have the ability to discharge the energy from the transformer. So that's why you have to use a specific instrument for that. So, and once you finish the test, by saturating or charging this energy here, you are magnetizing the transformer. So you also need to perform a demagnetization procedure. So the actual DLRO doesn't have that either. So this very specific instrument is called the MTO, Megger transformerometer, and it can demagnetize and it can handle the energy properly. I think I run out of time, so...
Question.
Yes?
Does it matter what size of transformer? Is the same unit for the trax unit or whatever, will it do any size transformer?
So the main aspect is that you need to charge this energy, saturate the core of the transformer to be able to obtain the result. Until you don't saturate, you are not able to
Is it a time
obtained.
thing? Is it just
So
time?
it's gonna be a time thing. So a winding resistance test is always a test that takes time. Now, the higher the current, the better, but it's not only the current, it's the voltage that you have to supply that current. So, the minimum requirement, or the standard tells you that you need at least 1% of the nominal current of the transformer. With 10 amps, you are basically kind of in the 80% or 90% of the transformer population to do that. So most of the transformers, you can do it very easy with 10 amps. We have another unit that has 50 amps that can give you the kind of the higher percentage of transformer population that you can test.
But in the low voltage world, the 10 amps.
10 amps
Plenty.
is more than plenty. And there's techniques that can accelerate the time of the test by doing, it's actually called dual injection. So you circulate the current through not only the primary winding, but the secondary winding. So this is the technique. And that way you are circulating current through the core, around the core, twice, and you're using the turns ratio of the transformer to increase that saturation level in the transformer, so that accelerates without using higher current. That's something that you can use there. So we have the winding analyzer, Megger winding analyzer. This does turns ratio and winding resistance. And we have separate instruments for the Megger transformerometer. So this is the 250, and we have also the TTR that can do turns ratio of a transformer. So we have like multifunctional instruments that can do the test, or discrete instruments that can do the test separately. And we have them at the booth if you want to stop by. Okay? As I said, I had more slides than time, so thank you so much.